For the last section this morning, we have one speaker, Davide Pigoli from King's College London. You see the title of his talk.
Thank you very much, and thank you to the organizers for the invitation. So this is part of a joint work. Yes.
Can you put the light down so that we can see the screen better?
Can I put the light on?
Oh, they all
yeah, they are coming down. Thank you. So this is part of a joint work with Pantelis H. Pantelis, John Aston and John Coleman from the Phonetics Laboratory in Oxford. And this is the current state of a project which has been going on for a few years now, which has the aim of analyzing speech data in linguistics. So the outline of the talk is I will give you a very short introduction to the problem, so why we are interested in speech data in linguistics, and then I will discuss how we want to model this data and how we developed a few methods to check some of the model assumptions we have from a linguistics point of view, and finally the final goal of this presentation will be to explore some change between pairs of languages, and I will discuss in a moment why this is interesting. So as I was mentioning, this is the current state of the project. We explored a few different directions in the past years. I'm going to discuss what we are doing at the moment, and why we think it could be of interest. So I realized I uploaded the wrong presentation. I apologize. So I'm going to just open up this new one. Okay. Yeah, it's exactly the same, but there are a few different changes, so essentially a few aesthetical changes, like this nice representation of what historical linguistics is looking into. So essentially, it's the branch of linguistics that is interested in exploring how languages develop in the past and how they are related today. So you have this kind of idea, mutuated mostly from genetics, where there is some ancestral language and modern day language are in some sense the results of an evolution from these ancestral languages. So the interest in this language development and language kinship is, first of all, of course, a cultural one, but also has some relevant consequences in other fields, such as anthropology, because they are helpful in understanding what are the relationships between different populations, sociology, and also in economic models, because language kinship is one of the parameters they use to understand, for example, trade, ease of trade between groups of people, etc. So this is the context, and what our linguistics collaborator really would like to do is to be able to reconstruct how this ancient language sound like. So be able to reproduce how a person, well, maybe not from Indo-European, but let's say a Latin speaker would pronounce some of the words that we see in classical text. So this is the final goal. I will not be able to arrive there today, but the way they want to do that is using reconstructing sound change between languages that are much more closer to us. So now modern day languages and languages from the near past from which they have some proxy. So for example, they are using German dialect from very remote region in the mountains to represent what ancient German can sounds like. And so if we are able to reconstruct the change from the modern day German to like say 19th century German, we may think to extrapolate the change onwards or backwards and reconstruct our older version of the German language would sound like. So of course extrapolation works up to a point, but they have clever way to reconstruct sign points over all this evolutionary tree to try to reconstruct the sound change. So this is their final goal, and today we are just talking about sound change between modern day languages. So if we are able to build this first piece in the machinery, then we hope to be able to one day produce the final result. Okay, so I already kind of give out what is the aim of our research. And in particular, today I'm going to talk about the analysis of this pilot dataset, which contains 23 speakers, so a bit of a downgrade from the 7,000 faces of the previous talk, but so we are not that lucky. We have only 23 speakers, and also the dataset is not that nice, because the sources of these recordings are heterogeneous, but anyway, we have the speakers from these 4 Romance languages, including 2 different versions of Spanish, one Castilian Spanish spoken in the Iberian Peninsula, and one is American Spanish from Mexico. So all these languages are part of a group of Romance language family, so all comes originally from Latin. And we're going to try to understand possibly how the sound change can be represented in this group. Okay, so up to now, what people are doing is they are looking at textual differences to compare languages. Well, not strictly textual, maybe differences, but at least differences in phonetic transcription. So this is the word for one in the 5 consider the 5 languages. You see between quote, you see the textual version of the word, and between brackets you see the so-called phonetic transcription. So the phonetic transcription is how linguistics, what you can find in the dictionary essentially of how a word should be pronounced. So that is contain information about the pronunciation, but it is a normative representation, which does not include, of course, all the variability that is present in the language. So the state of the art to explore changes between languages is to look at this phonetic transcription, while we want to use directly speech recordings. So we want to be able to explore direct sound change using speech recordings. Okay, so this so the first question is how to model this data. So first of all, what are these data? So this is an example of the word of a recording for one To be honest, I don't remember which language this was. I think French, but I'm not sure. This is what will be a representation of the recording if you simply plot the energy, the intensity of the sound over time. So this is something you can record from a microphone, you can record from your laptop. There are lots of applications that allow you simply to record this kind of data. Now the problem is that it's not possible to explore linguistic changes directly on using this representation. And the reason, if the technology support me, I'm going to try to make you hear the reason about that. So I'm going to play first the word for the recording from a Portuguese speaker. So you see, okay, this is too much. So you see, you can hear, okay. Then I can play a recording from a French speaker. Okay, so if I try simply to take the average between these two sounds, so the midpoint between the two vectors, this is what I get. So you see it's a superimposition of the two sounds at half of the volume. So this is in no way what from a linguistic perspective is the midpoint between two pronunciation or two words, two pronunciation, two sounds that are pronounced by speakers. So we need to find a different geometry, a different representation on which we can explore this change. Yes?
The fact that it's a man or a woman speaking, does it make any difference in the shape of the curve, or because it sounds really different?
Yes, yes. There is a difference, yeah.
So do you really want to average a man and a woman, or I mean?
Yes. So okay. So in one sense, yes, because if we are going to look at the change at the linguistic level, we kind of want to understand what is a property of a language, which does not depend if it is spoken by a man or a woman. Okay. So in this case, I just wanted to present you an example to see if we start from two points in this space of pronounced words. If I look at the midpoint, using this direct averaging in the time domain, I cannot find what will be a midpoint between the two. At the end, I will show you a path that goes from a man to a woman in a way that preserve the structure of the word. Okay?
Yeah. What would be the right, say, abstract or population definition of a midpoint? Because this is not even clear. I mean, you showed us the sample, and I agree that there's a problem.
Yes.
But what would be the theoretical quantity behind
so
to use later on?
Okay. So
why the midpoint? What is the midpoint?
the idea is that, as I was saying before, the idea is that there is actually an evolution in time. So okay. So these two languages have not evolved from one to the other. But let's say that we are looking at two different stages of evolution of the same language. If I'm going to the midpoint, I expect to hear the word that was pronounced in between the two time points. Okay. So if I'm talking how a word was pronounced in German in the 19th century and how the word is pronounced today, The midpoint, I expect that to sound like something that was pronounced in the 1950s. Okay?
This is a working hypothesis.
This is a working hypothesis. So this is the aim. This is the goal. We want to construct a system in which the average between sounds is pronounced is something that is linguistically sensible. Okay. So this won't be necessarily the case between two different languages, but still I want in between something that is recognizable as a word, to be able to build a let's say a proxy language, which is something in between the two. Now, of course, this is an abstraction in this case because there are no real in-between language. However, this language has common ancestors, so if we are going on the more abstract level, we may think that the midpoint is telling something about ancestors level of the common to the two languages. Although I won't be able to arrive at that stage in this talk. Okay, so this is a goal. It's not something that is necessarily true for the sounds, and as I've shown, if we simply do this, it's not true. Okay, so one way to address the problem, which is common in phonetics, is to move from the time domain to frequency domain. So we want to transform our data object from something which is simply a function of time to something that is both a function of time and frequency. And so we are going to do that through a local Fourier transform, and then we'll have some preprocessing so that we will be able to actually compare the different sounds across the different speakers. So the two steps, so first steps, we have a local Fourier transform like this. We have to choose a window for the locality of a Fourier transform. We used a Gaussian window with a width which is deemed reasonable by people working in phonetics. Of course, there is a trade-off. Sorry, there is a trade-off between the resolution in time and the resolution in frequency. You can have a lot of time point, but on a very coarse frequency scale, or vice versa, by choosing the width of this window. We choose one which sounds like a good compromise. So essentially, since we are working on sounds that are sampled at 16 kilohertz, means that we have around 160 sample points in each frame to compute the Fourier transform. Okay, so this is the first step, and then we actually extract from the Fourier transform the power spectral density in decibel, and this is what this picture is showing you. So we are throwing away all the information about the phase, and the reason is that our linguistics collaborator are adamant on the fact that there is no linguistics information in the phase. I'm not so sure about that after working for a while on this data, but at the moment this is what we are doing. Next step could be to do something on the phase as well. So then we are going to have some preprocessing of the data. So we have now one local Fourier transform for each word uttered by each speaker, and we add some denoising through discrete spline methods. This is a method for gridded data proposed by Garcia and quote by Garcia in 2010, and then we align the different spectrograms in time, because essentially we are worried that some speakers may have a different time dynamics in the pronunciation of the word, and we want to be able to compare like with like across the different speakers. Now we slightly modified the pairwise curve synchronization method by Tang and Muller, and the modification is in the fact that while we are aligning only in time, we essentially compute the discrepancy between two surfaces. So the discrepancy is two-dimensional across time and frequency, but the alignment is only in one direction, is over time. So it's a slight modification to adapt to our case. Now, I'm sure that all of you will have many suggestions on how to do things differently at this stage, and I'm happy to hear all of them. So essentially, I'm not married to any of these particular steps. There are different ways to do things. The important fact is that these two steps are necessary. So we need some denoising and we need some alignment. How you do that? There are a lot of different methods. You can pick the one you like most. In our, we actually tried also a few different methods, and the results do not seem to change drastically. But still, just wanted to say, the important thing is take care of this. You can choose the method that you like the most. Okay, so finally, once we have done all these steps, we get this object, which is the smoothed and aligned log spectrogram, so the power spectral density on the log scale. We have, as I was mentioning before, we have 23 speakers. Each of them pronounce up to 10 words. A few of them are missing. And these words are the numbers from 1 to 10. The sources of these recordings is heterogeneous, but our phonetics collaborators have put them together, do some careful cutting and paste so that we have these words resampled on the same sample rate, and so we can work on them. Okay, so this is the idea, and our working hypothesis to remember, the final goal is to model the sound change. Our working hypothesis is that if we look at this data that are essentially two-dimensional surfaces, we have a covariance structure which is a feature of the language, and while the mean is what identify the specific words. Now, this the reason why we have this working hypothesis with our collaborators is that you can imagine entering into a pub here in Cambridge, a very international place. So you can hear at a table someone talking a language you don't know. So you have two tables, both speaking languages that you don't know, but you can still recognize that they kind of sounds different. So how we our working hypothesis is that the covariance structure catch the way the language sounds like in general, while the mean is giving you individual words structure. Okay. So using this, essentially, we are modeling our log spectrograms as a mean which is word dependent plus some random surface. These random surfaces are independent across words, and their distribution depends only on the language. So of course we have mean 0 and some covariance structure that depends on the language.
Is this on the log spectrum?
Sorry?
Is this on the log spectrum?
Yes.
Then you need to do the mean correction. You did this, right?
What do you mean for?
Periodogram needs to be mean corrected to have 0 mean residuals. The lava model.
The
Probably you did this. Then
so maybe we can talk about this later. I
The mean plus an error, so
sorry.
no, because of
I
the
don't
log
understand
transform,
that.
the log transform. So the periodogram,
Yep.
the mean of the periodogram is the spectrum, but the mean of the log periodogram is the log spectrum minus gamma. This Euler transform.
Yeah, but we are talking about the mean across speakers here. It's not,
Oh,
okay. So it's a bit different. So it's not the mean over time but sorry, it's not a mean over frequency, but it's a mean across. So it's a mean across the population of uttered words, which include different speakers and different repetition of potentially different repetition of the same speakers. So I think this works. What is a bit of an approximation is that this independence, of course, because we have speakers. So we expected the errors to be correlated between the same speakers, but we are kind of ignoring that for a moment. Okay, so if you do that, well, just for notation, we defined also the residual log spectrum by removing the sample means for each word of each language, and so this is we have these residuals which treat them as a replicate within each language, ignoring the speaker's dependence. Okay, then we have a problem, which is essentially that this covariance structure between this four-dimensional covariance structure between frequency and time is too high-dimensional. Not computationally, maybe, but from the point of view of the estimation, because we have, unfortunately, we don't have 7,000 speakers. So with a number of speakers which is reasonable to expect in this kind of studies, estimating this four-dimensional structure in an accurate way is essentially a no way. So what we are doing is approximating that as a separable covariance as a product of two covariance function, one in frequency and one in time. Of course, this is up to a constant that we can put wherever you want. Now, we know that this is not necessarily true. So, no, it's not true in general. We even actually developed a separability test, and we saw that this hypothesis is not valid for this data. However, it is needed in practice to go on, so we treat them as a working approximation, and knowing that we are losing something about the codependence between time and frequency. Okay, so once we do that, well, you have possible estimators using marginal covariances for these two components. We use this normalization to get rid of the factor of the unidentifiability factor. Okay, so in the end, for example, these are the five frequency covariance functions that you can see for the five languages. So they look a bit different. Is this a significant difference, or it is just a fluke error? A fluke is just a noise production. So we are going to, in the next part of the talk, I'm going to explore this fundamental assumption of having a covariance structure that is a feature of the language and the mean that are water dependent, to see if these working hypotheses are supported by our data.
Can
Yes.
you just repeat this graph? So this is the covariance structure.
This is the
Across
the cross frequency, yes, across speakers
And across words.
and across words, yeah.
10 words.
10 words, yeah. Yeah, of course, this is a good point. This is what I'm saying that these are samples from language, but of course it's not a full dictionary of the language. It's only these 10 words in the pilot study. So the good point is that these 10 words are, even if from a content point of view they are the numbers, from the linguistic point of view they do not have any particular features, so they are kind of representative of the language as a whole, but still it's a very reduced dictionary, so in principle you would need to expand that to a larger dictionary. Okay, so now how to check this model assumption, in particular how to check the assumption on the covariance structure. So let's start from a much simpler case, two group scenarios with on a one-dimensional function. So we would like to test the hypothesis that the two covariances are equal against the one that are different. So to do this there are plenty of methods, but bear with me for a moment, and we see in general that if we, under the null, we can exchange curves between the two groups, and so if we have a way to measure the difference between the sample covariance operators, we can set up a permutation test, simply permuting the labels across the different groups and computing the distance between the sample covariance operators from the permuted groups, and that is giving us a distribution of the distance between the sample operators, and we can use that to compute p-value for the test. So we can use that to test the hypothesis. Now, of course, this is work if the group has zero mean. Otherwise, we are mixing together differences in mean as well. But you can apply that to centered curves, for example. Okay, so at this point will be the point where I will discuss different metrics for covariance operators, but of course yesterday we had a lot of talk about that, so I will try to go quickly, not to bore you too much. But the idea is that if you have classical functional data that live in L2, the covariance operator is a self-adjoint trace class operator, so there are different metrics that you can think of to measure differences between these operators. Some of them lives in a linear spaces. So, for example, if you use Hilbert-Schmidt distance or spectral distance, essentially we are embedding the space of covariance operators into linear spaces to measure these differences. But yesterday, Victor already explained us very well that we can actually consider the nonlinear geometry of the space, and we can propose metrics that take into account this geometry. So, for example, the square root distance, use the square root map to go from a tangent space and the manifold, or you can use the Procrustes distance, which essentially the way I think of it is mostly that takes into account the arbitrarity of the choice you have in the square root here, because of course you're not nobody tells us to choose the symmetric square root. You can use kind of Cholesky decomposition, for example, and when you go back to the original space, all the unitary transformation in the square root space disappears. So you have this kind of arbitrarity in the choice of a square root, and using the Procrustes distance, you get rid of that by looking at the minimum over the unitary transformation in the square root space. So yesterday we already talked a lot about this metric, so I want to say more about that, just that I'm going to use the Procrustes distance from now on to do everything essentially. Okay, so then we can generalize this idea to test for different groups. We can, as long as we use as test statistics the variation with respect to some center point, and how we define the center points between different covariance operators. We can use the sample threshold mean, and again, so once you have the distance, we can look at the barycenter with respect to the distance. So if you use Hilbert-Schmidt distance, you get the traditional pooled covariance function. If you use the square root distance, you get the square of the linear average in the square root space. While if you use Procrustes distance, you don't have any explicit solution. You need to solve the generalized Procrustes problem using the algorithm that Victor described yesterday. Okay? But still, it's pretty fast, so we don't worry too much about that. Okay, so once you have that, you can set up the permutation test, simply again permuting the labels, and we compute a test statistics for each permuted sample, and we look at the p-value as proportion of the permuted test statistics that are larger than the one from the original sample. Again, all of this works for zero mean curves, otherwise you need to center that. Since anyway the properties are asymptotical for this test, so we don't worry about that too much. Okay, so I talked a lot about distances for covariance operators. If you want to do the same for the mean, well, that's easy. You can use the L2 distance between the two surfaces and replicate exactly the same procedure. I will not spend more about that. Okay, so results. So if we test the quality of covariance operators between frequency across the world for each language separately, we can see that we don't have evidence to reject the null hypothesis that the covariance operators is the same across the words. While if we compare between languages, we have strong evidence to reject the hypothesis that they are equal. Now, of course, you can object that this may only be a function of the power of the test, since we have split the samples here. But I would say that at least this shows that as a minimum, this shows that there is no point in trying to model word-specific covariance operators using this data. So if we have, again, larger data sets, you may want to go look into finer differences, but at least in this data, we have no evidence to move away from our working hypothesis. So similar results, well, essentially the same result is for if you test for the covariance between times. If we test for the mean, there is this is the only slight hiccup. So for some languages, there is pretty good evidence that there is difference across the words for the mean, while for someone, for example, Portuguese, that's not that it's not that evident. However, Portuguese is kind of a bit of a problem in this data set. We have fewer speakers than the other languages, and also the quality of the sounds is not that great. So this is probably a limitation of the data sets more than a problem with the linguistic assumptions.
Can you repeat the issue with this? I mean, what's the difference if this is true or not for your covariance analysis?
No, for the covariance analysis, nothing changed. But since I'm going to use both mean and covariance to look at the sound change later, this will matter a bit. Although, so it won't matter in this. So I'm still using the more conservative choice of modeling separately the mean for each word. If it was true, although it's improbable, but if it was true, you could save some, you could do something more efficient and borrow information across words for the mean, but that's not really the case, and still in any case for many languages, we have evidence that that's not the case. So, okay, so finally we can put everything together and try to look at how to describe the change in sound between languages. So I'm going to spoil everything now. I'm going to give you the final results in a slide, in the first slide. So this is the idea. And of course this draw a lot of parallels with what Victor was talking yesterday about transport from one population to another. Here we were considering both the mean and the covariance structure, and the idea is that we can decompose the sound generating process for one language and one word into the mean for the word plus some speaker dependent residuals, which is modified by the covariance in frequency and in time proper of the language. Okay, so of course this is rigorously true if it is a Gaussian process. Everything is determined by the mean and the covariance. If as it probably is the case, these are not Gaussian process, we still have some additional information that is there in the residuals, but that's okay. So what we are going to do is essentially taking two different sound generative processes from the two languages and move this speaker specific residual from one language to another to see how that speaker would sound in a different language. Okay, so mathematically, of course, we need to invert this time and frequency covariance operators, and that is a problem because, of course, these operators are not invertible in general. However, what we do in practice is simply to truncate the covariance operators to some level where we can invert them safely. Now, this is not the most elegant thing to do. Jim probably will tell me that I should estimate the inverse directly, but this is what we are doing at the moment. So happy to hear any suggestion about this. Still seems to be working okay. So okay, so this was the general structure of the sound change from one language to another. So essentially looking at how an individual speaker would sound if we move him or her from one group to another group. And but since we want to actually explore how the path of this sound change is, we need to reconstruct a smooth path from point A to point B. So in our yes.
So you keep the exact same residual when you.
Yes.
Is there a reason? I mean,
Yeah, the reason is that what we want to look at is how the individual speaker would move following the language path. Okay?
oh, but are you sure that the residual would be the same?
No, the residual won't be the same because the speaker is not in that language. But so if you think of it as a standardization, you can see this this operation essentially standardized out the language and report all the speakers in the same reference system. So I'm using the residuals for that speaker to produce a process from the second group, a group in which that original speaker is not. So that residual is not in the original group because the speaker was not there. But if a speaker, it's kind of, if the speaker was born in that group, that would be what their residual was.
So you're assuming that the distribution of the residuals is the same in every language? Or?
Yes, yeah, essentially yes. So I was in second order approximation. We can we can try to adjust for more, but yes, the idea is that once you essentially remove the covariance, rescale with respect to the covariance structure is so this is the key. The key point is true that these covariances contain the information about the language. If it's not true, essentially we are missing a lot here, and it may well be the one interesting thing would be next step look at what we are missing and how and what is that, okay? But if it is true, or at least if it is a good approximation that this covariance structure contain the feature of the language, then we can expect the residual to be language agnostics, essentially. So another way, another thing we did, instead of projecting one speaker along this path, is to actually look at the residuals which is closer. So look at the residuals in the second language and pick the one that is closer to the residual of this speaker, and then essentially interpolate linearly the path between the two speakers. And I don't think I have the sounds for that here, but the results weren't that different. That would kind of adjust for the fact that there may be a different distribution for the residuals.
Because it could be that the speaker in a language is very similar to all the others, to the average guy, and in another language it sounds very different. But anyway.
Okay, I see what you mean. Well, but that would have been taken into care by removing a mean for that. I mean, so yeah, you can say. So again, it's up of how much information we are missing from looking only at the first and second order structure of the distribution. So if it was a Gaussian process, you wouldn't have any information left, okay? But of course, in general, you will have some additional information there, and it depends how much is that. But I agree, it's a good question to look into, and it's something we should do. Yeah. Okay, so the final step is reconstructing a smooth path from point A to point B, essentially smoothing or interpolating individually all the different components in this model. So for the mean, we can simply use a linear interpolation or extrapolation. for the covariance, we're using a procrustes geodesics, which has this form. Essentially, it is a linear in the square root space as long as you match the starting and end point covariances using the optimal matching from the gram matrix. So this is what we did. We saw yesterday there is a different approach to build geodesics for this space. Hopefully they will be equivalent. Otherwise, we may see what happens using their methods as well. Okay, so for example, if I move from the French on to Italian uno, I have this smooth path for the mean, smooth path for the covariance in time, and smooth path for the covariance in frequency. Now I can also include, for the speaker, for the residual part, I can even simply shift a constant residual if I'm thinking about moving individual speakers along the path, or I can match two similar residuals where similar can be interpreted in different way, can be the closest one or can be the one that are in a similar position in the residual of the distributions, and I can interpolate them. And that will give me a final sounds path. So I'm going now to produce a few sounds paths. Now, going back at the beginning, I told you that we throw away the phase information. So this kind of byte has here, because of course to go back to the sounds, you need phase information as well. And despite what our linguistic collaborator said, not any phase works. It needs to be the phase of the word. And so here what we did was using the phase of the starting point for all the path. And as you can see, it's true that you hear the linguistic change anyway, even if the phase is the wrong one at the end. So in that sense, our collaborators are right, but still we need phase information in a sense. That's something to bear in mind. So for example, this is the path from a French speaker pronouncing the word cinq to a Portuguese speaker pronouncing the word for 5, cinco. Let's start again. So you can see move from cinq to cinco, although the final quality is not very great because of this problem of the you see you here become cinco, but the final quality is not that great because the phase is still the one from the original one. But still we can recognize it's a recognizable word, and it is a recognizable path between the two. This is a second example, going from the word for 7 in French and the word for 7 in Portuguese. I'm not able to pronounce either, so just let you. Again, the quality of the sounds degrades because of a phase problem, but apart from that, it's the word is preserved. Okay, so this was what I wanted to tell you. So essentially, to sum up, we presented one possible approach to introduce speech data into the analysis of sound of cross-linguistic sound change. Now, of course, we are treading new waters here, so there are a lot of different bits and pieces that you can do differently, from the pre-processing to modeling assumption to different choice in the sounds process, but still I hope I show you at least that there is a potentiality here, but also there are some challenges that needs to be taken care of. So possible future direction, so of course statistical properties for this sound change, and probably here the work done by Victor and co-authors may be a lot of help. And then how to deal with phase component, which are ignoring, and we would need to generalize this to broader dictionary setting. So thank you very much for your attention.
Thank you very much. Are there more questions? I know.
Actually, two questions. The first one, what would a PCA analysis give here? Is this compatible? Does it make sense? I'm just spitting it out of the blue.
So it depends. So first of all, which PCA analysis? Because now, of course, we have a covariance function for each groups. So you're thinking about PCA cross covariances, or the PCA from each individual language.
Well, you could do a functional PCA analysis of your time frequency object. Right?
Yes, putting everything together.
Then maybe see if in the first few components you get information to. I don't know.
Yeah, that's a good idea. We didn't try that. Yeah. No, we didn't try that. Yeah, it's possible.
And the other question I had: could you use the time frequency objects and relate it to what people did in classification, that you would use this as a classification problem and then kind of construct a transition between differently classified.
Yeah, that's something I'm exploring at the moment. So yeah, that's something I'm looking into it, and I hope will give something useful.
Although it may not make much sense from a linguistic point of view, if you were to transform from one word in one language to a completely different one in the other language, so there's a much more dramatic change, then you could see the effect of perhaps how the metric would behave, the different metrics might behave quite differently. I just wondered whether you've done that, because they to me, maybe I haven't got very good hearing, but they didn't sound that different at the beginning and the end.
Oh, really? Okay. Well, we tried with different words, and that works. So that works more or less in the same way, because different words means only plugging in different means, but the variation in the covariance is still the same. What probably could be interesting is looking into more different languages. So, for example, if you look to Chinese, for example, you can expect that the covariance structure to be completely different, not only some small variation in where is the high frequency region or something like that. So, yeah, that probably would show more what you were saying. Yeah.
Any question?
Yeah, just one thing. So at the very beginning, when you play sort of the two words over each other, it seemed like this is sort of an unfair comparison, right? I mean, so the thing is, because in your method, this residual question, you use the same residual as you were moving this word along, right? So in some sense, these sort of individual level characteristics seem like they were kept in the word, as opposed to taking two words pronounced by two different people. So I mean, I'm just wondering, is there something which is sort of a more fair comparison to do with the?
Oh yeah, I can, as I was saying, I can plug in a different residual from the other language, and I will get something very similar.
Yeah, I mean, this is fine. It's just at the very beginning when you were trying to sort of.
No, I see what you're saying. Yeah, that was just an example to show you how sounds work like. But I can show you. I can play a comparison using original word residual from the second group, and that will sound even better. The path. Because it's because of course then I can use also the correct phase at the end, and so I will even have a better sound reconstruction, but still would sounds like something that move linguistically from one to another. So I apologize if the sound quality is not good enough to appreciate that here. But
then that's maybe related to your question, because the words are so similar that it doesn't matter. You should take the same residual or whatever, because they sound very similar. I mean, un, it's very similar to each other. So.
Well, you said at the very beginning that they were different because they were male and female. So, yeah,
in the residual.
Depends.
Information that's in the residual, right? So this is. I mean, I think it's right. I think it's right actually to use the residual, just because those characteristics that you don't model, right, are still sitting in there. So.
Yeah. No, sure. I mean, you can do both. We did both, and so it kind of depends a bit what you are trying to understand. I think. So on one hand, this projection of one speaker is also something that potentially has at a certain time in the future also practical application on sound modification for from a speaker trying to modify their voice or something. While using true speakers from beginning to end, it's probably more a more realistic path from the two present group. Although that's also more, I would say, it's also more relied on the actual specific samples that you got.
Okay, I think we should stop now and we are ready for lunch. Thank you very much.